S. Second thing, so I'm going to be using a lot of terms that are going to look quite the same as those used in symplectic geometry. However, they will actually denote the LCS generalization of those terms. For example, here, exact Lagrangian is actually exact in the LCS sense, not the symplectic sense. Finally, a bit more about the philosophy of the talk. So 20 minutes is a bit short to delve into anything too mathy, if you will. So really view this talk more as an introduction to LCS geometry and to some of its problematic, and really kind of more an encouragement for you to, like, I don't know, come and do LCS geometry in the future. It's quite a new field and not much is known. There's a lot of things to do. So the plan for this talk, is going to be, so first an introduction giving you the basic definitions and some examples. Then I'm going to talk a bit about the nearby Lagrangian conjecture in LCS geometry. And this is going to come and motivate the last part for this talk, which is going to be essential Liouville chodes, which seem to be some kind of LCS variants to the Reb chodes of contact geometry. So LCS manifolds. So this whole story started with like Lee in the 40s. He was already kind of thinking about LCS geometry. Just as an aside, like the field then went to kind of hibernation, and interest in LCS geometry only peaked back again quite recently, especially as far as topology is concerned. So anyway, so you want to do Hamiltonian dynamics on a manifold. And so maybe the first thing you're going to do is like ask for the transition map to preserve exactly the canonical symplectic form on R2n. So C is equal to IN. And this is going to give you symplectic geometry. Now, this means that the Hamiltonian equations are going to be preserved. However, you can just ask for the general form of the Hamiltonian equations to be preserved. And this is translated by letting C be some other constant, although positive. And this is going to give rise to LCS geometry. Now, this definition, well, true, is a bit unwieldy. And so for us, an LCS manifold is going to be a triplet M omega beta with M to n dimensional manifold. Omega here is going to be a two-form that is going to be symplectic up to some conformal factor that is going to be locally defined, as the name, locally conformally symplectic. And beta is going to be some gluing data for the mapped GUs. More precisely, beta is going to be equal to minus DGU. Now, more specifically, we're going to be interested in exact LCS manifolds. So again, it's a triplet M lambda beta. M is still going to be a 2n-dimensional manifold. Beta is still going to be our gluing data. But here, lambda is going to be a one form, such that the differential is going to be symplectic, again, to some locally defined conformal factor. Now, it would make sense to say that M is locally conformally exactly symplectic. However, just exact LCS rolls off the tongue much better. So this is what we're going to go with. Now, the submanifolds that we're interested in are the exact Lagrangian submanifolds, or to be a bit more precise, beta exact Lagrangian submanifolds. So those are actually submanifolds such that, like, if we abuse the notation a bit and call lambda Liouville form, it's not, but let's imagine it is, then L is just going to be a Lagrangian submanifold up to some locally defined conformal factor. Now, again, lambda is not exactly a Liouville form, and so this whole definition is a bit unwieldy. And so we're going to be using the alternative fact as a definition. So L is going to be a beta exact Lagrangian if and only if there's some globally defined F on L such that the pullback of lambda is going to be equal to df minus f times the pullback of beta. So this sort of twisted differential is going to be written d beta f. Now, a couple of examples. So the first example, maybe in LCS geometry, is going to be exactly almost the same as that of symplectic geometry. You take a manifold, you take its cotangent bundle, it has a canonical uval form, and well, here there's like a choice of beta on omega 1 of m that is not going to be canonical. But it's still going to yield a triplet C star m lambda and pullback of beta that is going to be an exact LCS manifold. Now I hear you ask, well, locally symplectic and LCS are exactly the same. Well, up to a conformal factor, but doesn't exactly matter. And first example, also the same. So is there anything different? And well, the difference is perhaps best illustrated through the following example. So if you have a contact manifold M alpha, alpha being the contact form, and then you can just like multiply your manifold by S1, and then you get an exact LCS manifold. And this is going to be called the LCSization. So apologies for the handwriting. I mean, there's a reason everything is on Beamer. This is going to be called the LCSization of M. And to be a bit more even explicit with this example, so this means that S3 cross S1 is actually going to be an exact LCS manifold. Now keep in mind that like S3 cross S1 has no symplectic structure. So this whole LCSization process, well, it also gives us examples for Lagrangians, sorry. So you start with a Lagrangian and you just multiply it by S1, and voila, you get an exact Lagrangian manifold. Now, this all should come together to really hint at the fact that LCS geometry is to contact geometry what contact geometry is to symplectic geometry. Now, with this, we kind of conclude the introduction, but before we continue, just a point about the conventions. So exact Lagrangians of symplectic geometry will always be called zero exact Lagrangians. And M and L will always be close connected manifolds of dimension n. Now, this is important because a lot of things I'm going to say in the rest of the talk are going to be completely false if this is not assumed. Beta is going to be a closed one form on M, and lambda is going to be the canonical uval form on T star M. Also, the various pullbacks of beta are going to be called beta just for clarity's sake. Now, okay, you're doing symplectic geometry, you're interested in exact Lagrangians, and so perhaps like one of the most important questions that is still open is whether or not the nearby exact Lagrangian conjecture is going to be true. So bear with me for a moment, like those are most certainly reminders for you, but there's a point to all of that. So if you take a zero exact Lagrangian, the nearby Lagrangian conjecture state that this Lagrangian is going to be the image of the zero section by a Hamiltonian isotopy. And in standard symplectic geometry, this is interesting because you have the Weinstein neighborhood theorem, and when you combine the two, this means that if you have like two exact Lagrangians that are close to one another, then they are going to be Hamiltonian isotopic. And this is kind of really good for us in LCS geometry because we actually have the LCS version of the Weinstein neighborhood theorem. Just as a quick aside, like, so this was proven kind of fairly recently. So just to illustrate my previous point that like interest as only in LCS geometry is only peaked back again very recently, and like there's a lot of things to do. So we have the Weinstein neighborhood theorem in LCS geometry, and then this kind of motivates us to kind of start digging in the direction of the nearby Lagrangian conjecture in LCS geometry. So is it true that for beta exact Lagrangians, then they're going to be the image of the zero section by Hamiltonian isotopy, well, of LCS type, but whatever. So maybe a bit of a spoiler, but this is going to be false. Now, well, okay, just assume I didn't spoil you the rest, but like, so we're at this point, and so well, trying to prove something that is still a conjecture in symplectic geometry and a generalization of symplectic geometry is a tad bit ambitious. So maybe we should focus on a theorem that's already has been proven. So, for example, the Abouzeid-Craig theorem, which states that zero exact Lagrangian and cotangent bundles. If you have a zero exact Lagrangian and cotangent bundle, then the projection is going to be a simple homotopy equivalence. Now, this is also like a bit complicated as a theorem to prove, so let's focus more on a corollary. If you have a zero exact Lagrangian, then the canonical projection is going to be an equivalence in homology. Now, the translation of this theorem in LCS geometry would just be to swap out the beta exact or zero exact for beta exact. And so the question would be like, is the projection of a beta exact Lagrangian quasi-isomorphism? Now, there's also like a slightly less naive translation, which would be to also swap out a single homology for most Novikov homology. Just because, well, most Novikov homology has already been successfully used to prove some statements of symplectic geometry in the LCS setting. And well, unfortunately for our two quote unquote translation of the corollary, well, they're going to be false. So you have a manifold M and a beta exact Lagrangian in the cotangent bundle of the manifold, such that the projection is neither going to be an isomorphism of singular homology nor an isomorphism of most Novikov homologies. And well, this kind of means that we have to reevaluate our goals a bit. So under which condition is the projection going to be an isomorphism of single homologies, or also under which condition is it going to be an isomorphism of most Novikov homology? So for this talk, we're really just going to be focusing on like this spot here. So, okay. So at this point, well, projection is not necessarily an isomorphism, but how bad can it be? So there's like the following lemma, which is very easily proven, which links so on the right, remember that we have the LCSization of the jet space, and on the left, we have the cotangent bundle of M cross S1. And so this means that in as far as LCS geometry is concerned, LCSization of jet bundles and cotangent bundles of the manifold times S1 are exactly the same thing. And this is useful because it kind of leads to a whole lot of examples. So here, for example, if you forget for a moment that we have phi here, so you will recognize the equations for a Lagrangian, a trivial Lagrangian knot, and the jet bundle of the circle. And if you add back phi, well, you have a d phi exact Lagrangian and the cotangent bundle of the torus. Now, obviously, this Lagrangian is like the projection of this Lagrangian is going to be of degree 0. But you can also use the lemma to build the projection of arbitrary degrees, and this is a bit more involved, but you can use it to build like Lagrangians whose Euler characteristic is going to be different from that of the basis. So far, so bad, right? Like the projection can be like arbitrarily like far from an isomorphism, if you will. However, do keep in mind that, well, the projection was linking the behavior of jet spaces to the behavior of cotangent bundles. And so this is kind of good for us because those things like in contact geometry, ruptures, right? And when a Lagrangian in jet space has no ruptures, then the projection is going to be simple homotopy equivalence, where the projection on the base space is going to be a homotopy equivalence. And so this gives us a direction in which to dig. Is there something in LCS geometry which plays the same role as ruptures play in contact geometry? And the answer seems to be, well, yes, and those are essential U-virtuals. Now, what are essential U-virtuals? So the definition, as stated here, well, it looks a bit atrocious, but let me carry you through it. So you take a Lagrangian L and the cotangent bundle of M. And so recall that being a beta exact Lagrangian means that there's a globally defined map F such that d beta of F is equal to the pullback of lambda. Now we add the following technical assumptions. So F is positive and beta is not exact. So with all this, with our technical assumption, take 2 points in the Lagrangian that lie on the same orbit of the Liouville vector field, and such that this inequality is verified. Then the segment between those 2 points is going to be called the unessential U-virtual. Now you ask, well, wait a minute. So here, this is some kind of primitive for the pullback of lambda. Well, twisted primitive, but it is a primitive. And well, in the normal case, if you didn't have this twisted differential, we have the choice of a primitive. And so what tells us that this quantity right here is actually well defined for all the primitives. And so this is a consequence of the following proposition. So if beta is not exact, then there's going to be exactly one F such that d beta F is going to be equal to the pullback of lambda. And this is a consequence of the following theorem, which states that if beta is not exact in M, then the pullback of beta in L is not going to be exact. And the following fact, which states that if beta is not exact, then d beta H is equal to 0, if and only if H is equal to 0. So combining the theorem and the fact, you get the proposition. So now that we're reassured that our U-virtuals are, well, our essential U-virtuals are actually a well-defined quantity, well, we can say the following theorem. So if a Lagrangian L has no essential U-virtuals, well, with also like keeping in mind that we have technical assumptions, if a Lagrangian L has no essential U-virtual, then the projection is going to be a simple homotopy equivalence. And so in your mind, just like swap out the LCS language for the contact language, like you take a Lagrangian in jet space, and if it has no rupture, then the projection is going to be a homotopy equivalence. And this kind of illustrates like the parallel between like essential U-virtual and ruptures. Although like the parallel goes also a tad bit deeper, because if you take, for example, like a Lagrangian in the jet space, and well, with alpha also the canonical Liouville form, if you take the lift of if you take the lift of the Lagrangian and T star of M times S1, and you take its essential U-virtuals, then projecting back the essential U-virtuals in the jet space are going to give you the ruptures of L for the contact form alpha over S being the coordinates in R. And also do note that also do note that the Reb orbits for this like quote unquote twisted contact form are going to be arbitrarily close to the Reb orbits for the normal contact form, for the canonical contact form, when S becomes arbitrarily big. So we end up by noting that we gave a partial answer to the question, if we do not have any essential dual shorts, then the projection is going to be a homology equivalence. And this is not a if and only if, for exactly the same reason that like you have Lagrangian with red shorts for which the projection is homology or homotopy equivalence. And so this concludes my talk. Oh yeah, sorry. Yeah.
Thank you. Are there any questions for Adrien? Maybe you could show again the definition of essential chords.
Sure, it is.
So what's special with one in this definition? Like, could it be another? Yeah, what's special with one? Does
the story with this is, I mean, it stems from the proof of this, in which you build a you build a new dual form for which your beta exact Lagrangian is going to be actually a zero exact Lagrangian for this new dual form, and then you apply Moses' trick to just get exact Lagrangian for a zero exact Lagrangian for the canonical dual form, and the one stems like it appears as a condition for the existence of this this dual form that you construct, that you build.
Mm-hmm. Okay. Are there any other questions?
And what happens when you come to the universal cover? So which kind of structure do you have?
Oh, so this is like the interesting part with LCS geometry. So if you actually just go to the integral cover of beta, then everything becomes symplectic. And this is an interesting part because do I have white space somewhere? Here is white space. So the thing that I omitted to mention is that alternative definition, you have the triple m omega beta. So beta omega 1 of m closed, omega non-degenerates, two form. And this is going to be actually LCS manifold when d omega minus beta wedge omega or omega wedge beta wedge omega, or whatever. I mean, there's like sign maybe is equal to 0. And so when beta is equal to dg, then E minus G d omega minus dg wedge omega is just going to be equal to d E minus G omega, right? So as soon as you go to the integral cover of beta, everything becomes symplectic.
But it's not compact anymore.
But it's not compact, and this is like a bit what is unfortunate. And so, yeah, it's going to like
Lagrange becomes usual Lagrangian. I mean, this but the exact Lagrangian on the universal cover is just usual Lagrangian submanifold or something else.
exact Lagrangians of the universal cover are just, sorry?
So what happens to beta exact Lagrangian embeddings on the universal cover?
So those twisted like LCS exact Lagrangians, they become actually genuine exact Lagrangians in the universal cover or even the integral cover of PR.
I see. And my question is, can you in this language say what is this essential Liouville chord or whatever definition you?
I haven't actually like thought much about it. So I wouldn't want to say anything too false, but the Liouville chord is essentially going to kind of measure how quickly your map F grows along a Liouville orbit. And it might be linked to like maybe how many turns you make of like around your manifold or something. In which case, like when you lift your LCS exact Lagrangian to the integral cover, the universal cover, you are going to have multiple sheets of exact Lagrangians. And so it might be it might give you some idea on like maybe how many sheets there are. I don't know.
Thank you very much.
Any other question? Okay, so let's thank Adrien again. Thank you, Adrien. And then the next one, I think, is Adi.